Saxon's Trigonometry, Lesson 13, about intersecting secants and tangents, products of chord segments, and products of secant and tangent segments, beginning on page 97. So section A is the intersecting secants, and we remember that a secant is the lines that cross through a circle, forming chords that go from side to side through the triangle. And because this is intersecting secants, you need two lines that are intersecting in order to have your intersecting secants. Now, the rule that you use with intersecting secants is an extension of what we've already talked about, where an angle, scratch that. If this angle and this angle are vertical and the same, we need a rule that helps us figure out the arcs that they cut. So even though they are the same, they're not coming through the center, so there is not a direct relationship to the arcs that they cut. However, when they cross inside, what you do is you add the arcs and you take half in order to get the answer for the angle. So if we start labeling these things as they have here, this one is X, this is 80 degrees, this vertically is also an X in degrees, and this one is labeled 40. Because they cross inside, you want to add the arcs cut, 80 plus 40, and this is the half part is where it does kind of connect to the rule that you knew before, which was that an angle that cuts inside is half of the arc that it cuts. Okay, so 80 plus 40 divided by 2, 220 divided by 2 should be, wait a minute, 80, 90, 100, 120. I knew that didn't sound right. 120 divided by 2 is 60 degrees, so X is 60 degrees. Now, example 1 asks you to prove why that rule is true. So I've told you the rule. You should write it down in your notes to have it as reference. And here is why it works. So let's go back to another, and I'm not going to draw the full lines as they're doing in their solution on page 98. I want to try to follow what they're doing with their labeling. So rather than drawing these as lines, I'm drawing them as chords. This is A, D, B, and C. And in order to do a proof, I typically need to have a triangle. So you can choose to put the triangle wherever. Again, to match what the book did, I'm going to draw the dashed line. If this were a formal proof, I would have my statements and then my reasons, but this is just kind of a walkthrough for why the rule works. So I'm not going to do the actual column. All right, they've labeled this one as angle 1. We know that vertically this is also angle 1. And then this is an angle 3, and this one is going to be labeled angle 2. I think those are small, but I hope you can read them. Okay. Now, I need to start finding some relationships between these angles that are marked. Now, we have not talked about this year, but you should have learned back in geometry class a rule which says that an exterior angle, one outside of a triangle, so this number 1 is outside of the triangle, or this one, either way, is the same as the sum of these two angles. Now, if you stop and think about that, that makes sense logically, because this angle and this angle form a line, which is 180 degrees. Triangle also forms 180 degrees. So if you take 180 minus 1, you get the degree for here. And if you do 180 minus these two, you get that same answer. So the rule is an exterior angle matches the sum of the remote, far away from angles inside. So we know that angle 1 is the same as angle 3 and angle 2. Okay, then we also know that angle 2 cuts this arc AC. Cuts AC as an arc. And then I could go ahead and kind of say the same thing the opposite direction. Angle 3 cuts arc DB. Now we have a relationship between the angles that are formed and the arcs that they form. So if I substitute in the information here with the angle 1 statement, instead of writing angle 3, I know that angle 3 is half of this arc because it's inscribed, so the rule says this angle is half of this arc. So we're going to substitute that in. Angle 1 is the same as half of DB plus from here, and angle 2, instead of that one, we're going to use this one, which is half of AC. So, and then if we separate that, we're basically saying that the measure of angle 1 is half of arc DB plus arc AC. And so that's what I said. Addition of the arcs divided by 2 gives you the degree where they're intersecting. Now, part B moves to intersecting secants and tangents. The first one shows you two tangents. That's a little crooked, sorry. They're crossing outside of the circle. Oh, sorry, that's not two tangents, that's two secants. Yes, two secants because they're crossing through, and you have an angle out here that is cut by this little arc and this larger arc. So the rule here, when they're crossing inside, we add. When they're crossing outside, we subtract and take half. So that's the rule here. And this is the same thing, applies the same for if you actually have a tangent touching one spot, I didn't get that quite there, and a secant crossing somewhere out here. So this X is going to be half of this large one minus this one. And it works the same if we have two tangents, which is what I incorrectly said over here a minute ago. Ooh, I'm having trouble drawing with my pen today. This should touch once, this should touch once. That makes it two tangents. So this angle should be the big one minus the little one taken in half. Okay. All right, now that we have the rule, example 2 says, prove that the measure of the angles formed by the two secants intersecting outside of the circle is equal to 1/2 the distance. So basically prove that it works this way as well. Okay, I was going to try to match the way they did it. Their intersection for their example on the top of 99 is over here, but I don't think this will confuse us too terribly much. We are going to create a triangle between, I think it's this way. No, I feel like that doesn't give me, but it should. No, they should be in two different places. Okay, yes, this will work. All right, so we are going to cut it into a triangle. No, because I need it with this being inside the triangle. You know what? Let's just redraw this. That will avoid tons of confusion. Okay, they are crossing here and outside. All right, so let me go ahead and label them. It's P, and this one is D, and C. B should be the closer one, and A should be the further one. And now that I have that labeled, it's definitely connecting here to form this triangle that contains this outer angle. So if I were trying to do it here, containing this outer angle, oh, it should have been this way. That's what I did backwards. Okay. Now that we have that sorted out, we need to label the degrees. So this outer one, they labeled 1. This one, they labeled 2. And then it doesn't really matter, but this one was 3 and this larger one was 4. Okay, so we know that angle 3 is the one on the outside. So angle 3 is going to match with the same rule we used before, angle 2 plus angle 1, because they are the remote interior angles. Now let's get the information about the arcs that are cut. So angle 2 is cutting the arc BD, so it's half of BD. Angle 1 is cutting AC, so it's half of AC. And since I want to solve for angle 1, I need to do a rearranging here and solve for 1. So to saying angle 1 is angle 3, move to the other side, minus the angle 2. And technically each of these should say the measure of angle 3, the measure of angle 2. I'm not doing that since this isn't anything formal, we're just talking our way through it. So now let's do the substitutions. Angle 1 that we want to solve for out here is, oh, just a second, I have 1 and 2. I didn't do 3. Let's do 3 because that's the one I actually need here. 3 cuts AC. Same thing, cuts AC. Okay, now we don't need that one. So angle 3 is half of arc AC minus half of BD. BD. And then we can do the pull out of the half. So that is your AC minus your BD in the arcs, and that's why the rule minuses. All right, example 3 and example 4 ask you to prove the other two, but they basically, so this format and this format, they basically work the same way. You're forming the triangles. So for excuse me, for this one, you're definitely going from the tangent over to create the triangle. It should be in dashed lines, but and then you use basically the same rule, and it's going to be the subtraction. This works the same way in example 4. The triangle that you would draw here comes across and connects this way, and then you can basically work that the same. You can walk your way through those other two examples. I'm not going to do it on the video, and I'm going to move on to example 5 on page 101, which is an actual solve here. So this gives you two crossing. They want you to find what x is. This one is 80 degrees, and this little one is 30 degrees. So we're going to follow our rule, which is 80 minus 30 divided in half. So that's 50 divided by 2. So 25 degrees is x. Example 6. This time it does a tangent and a secant. It wants x solved for. It gives you this side is 120, this one is 170. So when I go to do, they're crossing outside, I know I need to subtract and divide in half. The large one is 170. I don't have the small one, but I can stop and find it because I know that a full circle is worth 360. We're going to minus off the addition of 170 and 120. So 290 is coming off. That should be 70. Yes. So then we are minusing 70. 170 minus 70 is 100. 100 divided by 2 is 50 degrees is x. That's example 6. Now, part C is products of chords and segments. Again, their next example is prove that the rule, which says that when I have these crossing pieces, that what we do is we multiply the 3 times the 8, the lengths of those lines, and it will equal the 4 times the 6, the length of those lines. So the two chords will be the same in length and then their product. So they want you to prove why that rule, which we already had in an earlier lesson, works. So the basis behind this is on page 102 for their solution. And again, we need triangles, so they're connecting them here and here. And they didn't have any numbers because this was the proof, and it just said prove that this actually works. All right, so what I'm doing here is I'm saying that this chord is cut by this angle here, and here it's the same arc that's cut. So I know that these two angles must be the same. I know that these two are the same because they're vertical. That means two angles are the same. The third is implied to be the same. I now have similar triangles. If I have similar triangles, their sides form proportions. And that gives you, if we have these labeled, I'll just do the numbers here. It gives you 3 matching with, I believe it's 6, and 8 matching with 4. No, that feels backwards because it should be 3 times. No, it should be here. This should be 4. Yes, I flipped triangles. I broke the cardinal rule. Don't change the direction that you're doing things. I started with 3 from this triangle. I need to keep the top 4 from the same triangle. When I do the cross multiply, then 3 times 8 equals 4 times 6. And that is the chord pieces, and that's what they wanted me to prove. So now doing the same kind of thing in example 8, they give us 30, 40, x plus 20, and x plus 10. So we're going to follow the rule and do the cross multiply. So well, basically the multiplies. 30 times x plus 20 should equal 40 times x plus 10. Distribute. 30x plus 600 equals 40x plus 400. Moving the 30 over means I don't get a negative, so that leaves me 10x. Minusing 400 from 600, 200, divide by the 10, so x is 20, and that's what they wanted me to solve for. Okay, part D says, it talks about products and secants and tangent segments. We have a circle and a secant going through, and another connection here. All right, so this is labeled a 5, a 3, a 2, and a 10. So the rule that we want to get to here is that same multiplying of parts. Now in this one, obviously they were crossing inside the circle, so we use just the straight multiply rule. In this part, they're crossing outside of the circle. The rule is similar but not identical. The outside number, this 3, has to multiply with the length of the entire line, 3 plus 5, and that will match the outer piece 2 with the sum of its entire line, which is 2 plus 10. Then you can work your way through that and prove that those numbers actually do work out to be correct. In example 9, they ask you to prove why that rule works. And again, if you want to follow in example 9, where they cut their 2 triangles and they prove that they were similar, and therefore you had to have a proportion, and therefore this has to work. I'm not going to go through that here. It's just a lot more repetition of the things that we've already been talking about. In example 10, on the bottom of 103, they ask you to solve a similar type problem. They're connecting to the outside. This is x, this is 3, this is x, and this is 3. So following the rule, we take the outside part, 3. We multiply it with the sum of the entire line, and that will equal the outside piece times the sum of the entire line, and distribute. 9 plus 3x equals x squared plus 3x. Yeah, sorry, I was checking the next example to see where they were heading. I see that I have an x squared with some x terms here as well. So I am going to have to put this in descending order. I'm going to keep it equal to 0, so it's x squared. That means I'm moving this 3x over, and it cancels with this 3x, and I'm moving the 9 over, which makes it 9. At this point, I wanted everything on one side equal to 0 because I know with a squared, I'm heading to some sort of factoring, and I assumed I needed to do 2 different parentheses. Now, you can solve it this way, or you can change it back over to x squared equals 9, where this would have been had I not moved it. And how do you undo a squared? Square root the other side if you do that. So x equals 3. Now there is a rule which says, and we learned this with the quadratic formula, whenever you put a square root around something, you automatically and always put a plus and a minus sign. So there are 2 answers, a positive 3 and a negative 3. So what happens over here if I do actually split it into 2 parentheses? X and x forms the x squared. 9 splits to 3 and 3. I have no middle term, which tells me my signs must be opposite, one being positive, one being negative, to kill off the middle term. And also, I must have a positive multiplying with a negative in order to get a negative. And when you solve these, you get this one as a negative 3. This one moves over to a positive 3. Either way you think your way through it, you end up with both positive and negative 3 for your answers. This is why I was kind of looking. That was example 10, which took them all of page 104 to do. Example 11 does another proof. Again, I'm not going to do it. It's based on the triangles. They're similar. The half of the arcs, they form proportions. Same thing we've been doing. Once they've proved that this works, they give you an example. And so the new thing here is that the secant and the tangent didn't, it's obviously touching in one spot, so it looks a little different. We only have a part here, which in this example, they're labeling 8. This one is 12, and this one is x. The same rule applies because it crosses outside. So when I do x, it has to go with the x plus 12. However, this outer number 8 is the sum of the entire line. So I don't have an addition part, it's just the 8 times 8. X squared, 12x from distribute, 64. This one definitely needs to go to x squared plus 12x minus 64 equals 0 because I moved that over. Then I'm either going to factor it into 2 parentheses or complete the square if that's not nice and easy. So let's see if we can actually factor it. X and x. What does 64 split into? Well, 2 and 32, but combining those will not get me to 12. 4 and 16. 16 and 4 can get me to a 12, so let's try those. 16 and 4. Then my number in the middle is positive. The larger of these numbers must match that and be positive. How do I go from 16 to 12? I subtract 4, and the final thing to check is positive times negative is negative. Okay, I've not broken any rules. That works. So now we're going to solve. X is negative 16, or x is 4. Can I keep both of those solutions? Well, let's see. If I plugged in a negative 16 here, it works number-wise, but in the real world, can I have a line that is negative 16? I cannot. So the only answer we're going to keep is x is 4 because it does not break a real-world solution. And that is the final example in this lesson.